We have that's page 190, 7 questions on that page. You guys asked me to go over 3 of them, 4, 6, and 10. So we'll start with number 4. It says a pair of skis weighs 15 newtons down. What does that mean? What does that number that they're giving to us mean here? Yeah, that's the gravitational force on it, right? It weighs 15 newtons down. And we said technically weight is a downward force because it's a force of gravity, although we usually just take the absolute value of it because we don't usually like to hear a negative 15 newtons, right? So usually we just say 15 newtons, but it is the force of gravity, so technically it is downwards 15 newtons. We want to find the difference in the maximum force of static friction for the skis on a wet and a dry, snowy horizontal surface. And then, of course, we've got to go back to that table to get the coefficients of friction of wet and dry, snowy surface here. What do we got here? We know that we're gonna use the what is it? Is it kinetic or static actually? Static, yeah, it's static friction. Okay, the force of static friction, maximum force of static friction, that is, FSF max, which is equal to mu times the normal force. Now, the normal force, we're not told directly what the normal force is here. We kind of are, indirectly at least. Can anybody tell me what the normal force is or how to find it? Yeah. No, normal force is not mass times the force of gravity. Normal force is mass times the acceleration of gravity. So the normal force, for us at least right now, when we're dealing with horizontal surfaces and no vertical acceleration, the normal force will always be equal to the force of gravity, m times g. We have the force of gravity given to us. We don't know what mass is. We don't need the mass because we know what mg is already. This is mg, right? The force of gravity. Does that make sense? So we're going to say it's the coefficient of friction times 15 Newton for the force of gravity, and therefore 15 Newtons upwards for the normal force. What is the coefficient of friction of the skis on wet, dry, sorry, on wet snow? So we're going to say 0.20 for wet snow times 15 newtons, and that's going to give us a force of 3.0 newtons. Okay, for dry snow, sorry, that's 0.06? Oh, for dry snow. Okay, so for dry snow, we're going to say 0, oh, I see, for the coefficient of friction, you mean. 0.06, any numbers after that? No? 0.06 times 15 gives me, is it 0.9? 0.9? How many digits should I round it to? No. 0.06 is 1 digit, right? So the final answer should be 1 digit. 1 significant digit. Somebody in the other class said, not for this question, but for another question that relied on a piece of data from the table, it was 1 digit. Somebody said, well, shouldn't we go with 2 digits here? Because the 1 digit number came from the table, not from the question. Doesn't matter where we get it from, right? Okay. We go back to original data. If it's original data and we used it, we count it, regardless of whether we got it from the question itself or from the table. It doesn't make any difference. So the first one would be 2 digits, but the second one would only be 1 digit. Now, I guess technically, actually, we're looking for the difference, right? So what's the difference? 2.1 newtons, right? All right, the next one you guys wanted to go over was number 6. It says a biker and his motorcycle have a weight of 2,350 newtons down. Kevin, what does that correspond to? Yeah, it's the force of gravity acting down, but on a horizontal flat surface with no vertical acceleration, it's also going to be the normal force. So we know what Fn is. We want to find the force of kinetic friction as the motorcycle skids. Okay, as it skids, that's sliding, right? And sliding is kinetic. We're looking definitely for the force of kinetic friction. It's equal to mu times the normal force. Mu was rubber tires on dry concrete, 0.7 One digit? Okay, 0.7 times the normal force of 2,350 newtons. Now, if they give us the mass instead of the force of gravity acting down, then we have to multiply that mass by 9.81. But we're not going to multiply the force by 9.81 because it's already been done for us. 0.7 times 2,350 is 1,645 newtons, which we're going to round to one digit. What would be my final answer, rounding it to one digit? Yeah, listen, you got to look at that first number, right? Okay, look at the digit right past that. What's the number, the digit past the 1? It's 6. If it's 5 or bigger, we got to round that first one up. So it becomes 2 times 10 to the 3 newtons. And finally, we have our last question that you guys asked me for was number 10. It says a loaded dog sled has a mass of 400 kilograms is being pulled across a horizontal packed snowy surface at a velocity of 4 meters per second. Suddenly the harness separates. The coefficient of kinetic friction is 0.0500. Here we go. Here's a 3-digit coefficient. That's better. How far will the sled coast before stopping? Good question. Okay, good question. Some of you may have a vision for what to do with this question right now. Know exactly where you're going with it. And if you do, that's great. It's wonderful if you can see the whole question right now. But if you can't, that's okay too. You don't know exactly where to go with this question? Well, let's just follow some logical steps. First of all, let's ask yourself, is it group A or group B? It's group B, so we know we can't use V equals delta D over delta T. All of those other equations that we've learned are valid. Doesn't mean we're going to use them all because clearly we're not, but at least they're valid. What I want you to do now is write down your givens and then try something from group B that seems like it may get you something. And then try something else. See what you can do. We know the mass is 400 kilograms. Can you tell me what this is? This 4 meters per second? It's going to be VI, right? It's moving that speed and then it begins to slow down. Is there anything else that I have given to me here? What is it? VF is 0, good, because it comes to a stop, right? Anything else? We got mu K, good. Mu K is 0.0500. And we're looking for the displacement here, right? Okay, any ideas here? Somebody without the vision for this, somebody who I mean, you may know how to solve it now because you've gone through it, but as you were solving it, you know, you weren't sure exactly where you're going with it. Go ahead, Laura. Okay, force of kinetic friction. Good. Just stop there for a second. The force of kinetic friction is mu times the normal force. Is that valid? Yeah, absolutely. Is it going to help me? Probably. But the worst case scenario is that I do it and it doesn't help me. It's not going to give me the wrong answer. You don't have to know what you're going to do with the force of friction. But if you can find it, find it. Mu is 0.0500. The normal force is going to be m times g, 400 times 9.81. Notice, Simon, this time I'm multiplying those two numbers together because I've got mass, not the force of gravity given to me already like I did in the last two questions. What does that give me there when I say 0.05 times 400 times 9.81? 196.2 newtons. Thank you, Isaiah, for the help. Now, what do we want to do next? Get acceleration. All right, that works. Okay, and we're going to find acceleration by saying A is equal to F over M. Now, Laura made a good point just a minute ago. I don't know how many of you guys heard it. Said when we plug that into this equation, we need to make that force. Yeah, it's a very good point. A lot of people are going to miss that. When we calculated the force of friction up here, we calculated the magnitude of the force of friction, right? That's not what we want. We want the magnitude and direction. We want the force of friction. And it's opposing the motion, right? If we're moving to the north, then the force of friction would act to the south. So when we plug it into here, an equation that doesn't have the absolute value sign, we're going to plug in the sign of it as well, which is negative. Simon, you look like you're puzzled there a little bit. Well, if you're moving to the right, if it's moving to the right, that's the velocity, then what force is going to slow it down? Yeah, which is to the left. Right? So the force is going to be to the left. Well, if the force is to the left, it's a negative force. Right? I should have said north and south, not right and left, but you get the idea there, right? It's going to be a negative force. Now understand that when I calculate the force here, it's never going to be negative because this equation always gives me an absolute value. But when I go to plug it into an equation that doesn't have the absolute value, I should include a direction whenever possible. So we got negative 196.2 divided by the mass of 400 kilograms, negative 0.4905 meters per second squared, correct? All right, Laura, you seem to be the star on this question today, so tell me what I do next. Good. So we're going to rearrange that to solve for delta D here. I get VF squared minus VI squared over 2 times A. So what does it become? 0 squared minus 4.0 squared over 2 times negative 0.4905. 16 over 0.981, going to give me 16 point something. 16.1, 16.2? 16 even? Okay. The 2 digits, I guess it would be 16 anyways, right? Regardless of what the decimal place is. Okay. Good. And that comes out to be positive. Lo and behold, because the displacement is positive, even though the force is negative, it's moving in the positive direction, so we get a positive 16. Some of you may not have known where you were going with this question, started exactly the same way as Laura did. Some of you may have worked backwards and said, look, I want to find the displacement. I think I'm going to use VF squared. Okay, started with that equation, realized, oh, I need the acceleration. And then, oh, how am I going to get the acceleration from the force of kinetic friction? So what I'm saying is that Laura did it probably the way that I would have done this question as well. But if you try something else first, that's okay. As long as it's not something that's not valid, like V equals delta D over delta T. Try something. Okay, and if you find that you get something, great. If you find that you need something else to do that something, then do something else. And it's amazing how when we tackle questions like that, they often just fall into place. Okay, we don't have to always know exactly where we're going with it. They just fall into place. Yesterday we started something a little bit new, not new really, but just an extension of what we had been doing. We've been talking about friction and individual forces. Yesterday we started talking about multiple forces. Whenever we have a problem with more than one force acting, what do we do? What do we do whenever we have that force or that problem with more than one force acting? We do what? Yeah, but before we find the net force, what do we got to do? We got to draw a diagram. We call it a free body diagram. Okay, a free body diagram shows all of the forces acting on an object. Let's say we got a car, and the car is broken down. So there's a tow truck pulling the car to the right. But there's a force of friction acting on the car to the left. And there's a force of air resistance acting to the left. We would draw the force of the tow truck to the right. We would draw the force of air resistance to the left. We would draw the force of friction to the left. Can I draw friction up here, by the way? Yeah, I can draw it wherever I want as long as I have the right direction, as long as I have it roughly the right magnitude. Doesn't matter where I draw it, right? So I choose to draw it up here because if I drew it over here, diagram becomes a little bit cluttered. Whatever. Okay, whatever you want to do. Is there anything else, by the way, acting on this? Max? There is gravity acting down, yeah. We don't know how big it is, any of these forces are, but gravity is acting down. Yeah. And the normal force is acting up, has the same value as gravity. So what are we going to do with that gravity and normal force? Yeah, let's erase it or cross it off. Anything that balances something else, just get rid of it to simplify a little bit. Listen, this is good news that we can simplify those, because if we couldn't cancel those out, then we got a problem where we got forces on the x-axis and forces on the y-axis together. And we will learn how to deal with that in a little while, but right now we don't know how to deal with it. Good news is they cancel out. All of my forces are on one axis, on the x-axis. Now, what's the next step? Somebody said it before. Simon, was it you? What is it? Yeah, the net force. The net force is just like the analogy that we used with our paycheck here, at the beginning of this unit, the net force is the total of all of our forces, the sum of all of our forces. In this case, we'd say the force of air resistance plus the force of friction plus the force of the tow truck. By the way, what if Jackson is doing this problem and he names the force of the tow truck FTT, or he names it F3? It doesn't matter, does it? You can call it whatever you want as long as you know what your notation means. Now, if I'm looking for the net force, I'm just going to sub in my numbers and solve it, right? But if I'm looking for the acceleration, then what am I going to do? The net force is equal to the sum of the forces. What do we say on the first day of this unit? The net force is also equal to m times a. So if we're looking for acceleration, we're going to replace that F net with m times a, and then say ma is equal to the force of air resistance plus friction plus the tow truck. Plug in our numbers and solve. What do you got to be careful of here? Direction, positives, and negatives. All right, 2 questions for homework last night on page 132. Issues with either one of those? Yeah. We'll just do all of number 2 then for context. Okay. 2 says in a tractor pull, 4 tractors are connected by strong chains to a heavy load. The load is initially at rest. So let's draw this. Let's start drawing this at least here. There's the heavy load. We don't know what its mass is yet, but we know that it's sitting there on the ground. Yeah, Laura? Yeah. Tractors A and B pull with forces of 5,000 newtons and 4,000 newtons to the right, or to the east, I should say. So let's say FA. Let's say that's 5,000 newtons. And let's say FB is 4,000 newtons. I'm going to make that a little bit shorter because, of course, it's a smaller value of force. C and D pull with 4,500 and 3,500 to the west. 4,500 is going to be something like this. I'll call that FC. And FD is 3,500. Is that it? What else we got? What else we got here? Yeah, we got friction. Which way does friction act? Good? No, friction doesn't act down. Friction is a result of the normal force, which is of course, due to the force of gravity, the downward force of gravity. But friction itself isn't down. Okay, so it acts against any force. It's pulling it. We got forces pulling it in 2 directions, left and right. So it acts against which one? The left one or the right one? Jackson? Good. Whichever one has more force. If the force to the right is bigger than the force to the left, right? That means it's going to move to the right. If it moves to the right, which way is friction going to act? To the left. So I'm going to draw friction up here to the left. I can really draw it anywhere I want, but this is looking really cluttered with all the forces we have, so I'm choosing it to draw it up there just to make it a little neater. Right, Sebastian? Now, what comes next? Do we have any other forces? We do. Yeah. Yeah. I'm not sure what the value of the gravity and net force are, the normal force, sorry, but we do know that they balance each other. So it doesn't really matter too much. What's the next step? Add them up. Just like we add up all the things on your paycheck, the net force is equal to FC plus FD plus FF plus FA plus FB. Here we go. We got a problem involving 5 different forces that don't cancel each other out. Now, since we're just looking for the net force, I'm not going to replace that with m times a, but I could. I could if I needed to. FC is 4,500 plus 3,500 plus 1,000 plus 5,000. Simon, what are you saying there? Yeah, the ones that are going to the left are negative. Good. We add those up. I think we end up getting 0. We add those up. So the net force here is 0 newtons. If the load is initially at rest, will it start moving? No. because the forces are balanced, right? There's zero net force acting on it, so it's going to keep doing what it's doing. If it starts at rest, it's going to stay at rest. If it starts in motion, then it's going to stay in motion at a constant speed and straight line. Got it? Why are they pulling? It's like a tug of war with tractors. Good question. In a question like this, would it matter what the weight of the object is? No, it doesn't. Let's say the weight of the object is 10,000 newtons. Okay, mass times gravity, mass times 9.81 it ends up giving me 10,000 newtons. Okay, so Fg would be 10,000. The normal force would be 10,000. They cancel out, so it doesn't matter whether it's 10,000 or 100,000. It doesn't matter. Yeah, Jack. All right, I want to do one more question just to wrap it up for the day here. This one says, two athletes on a team A and B are practicing to compete in a canoe race. Athlete A has a mass of 70, athlete B is 75, and the canoe is 20 kilograms. A can exert an average force of 400 newtons forward. We'll call this guy A and this guy B. This one's going to be 400 newtons forward. I'm going to say force of B is 420 newtons. Can I draw that right there, or should I have drawn it over here directly on guy B? It doesn't really matter, right? Doesn't really matter. They're both accelerating the system, so it doesn't really matter where I draw it as long as they're the right direction and roughly the right length. There is water resistance of 380, so it's going to go back this way, about like this. I'll call it FW, but really you can call it whatever you want. Anything else? Yeah, we get gravity and normal force, right? When we define normal force, we defined it as the force of the, quote, ground pushing, quote, up at 90 degrees. What's providing the normal force here? It's not the ground. It's the water. It's the buoyant force of the water pushing up on the boat. But it's going to push up with the same rate as gravity, right? Because if it doesn't, what's going to happen? If buoyant force is less than gravity, then it's going to sink. If the buoyant force is greater than gravity, it's going to fly. Right? Next step. Next step. Atom. F net is equal to the sum of the forces, Fw plus Fa plus Fb. Now, since we're looking for the acceleration here, then what's our next step going to be? It's not going to be to plug in my numbers, but rather it's going to be to say F net is also m times A. Let's sub in my numbers now. Mass here is 70, 75, and 20, 165. We're going to use the total mass because it's the total thing that's being accelerated. Fw is negative 380, Fa is 400, and Fb is 420. 165 times A is equal to, I think that's 440. And 440 divided by 165 is going to give me 2 point something. 2.7, say? Meters per second squared, or you could say newtons per kilogram, right? Good. Okay, one question that you have for homework, just one, page 150. I want you to read through this question, but I want you to be conscious of something in this question as you do it. In fact, two things. There are two things in this question that aren't relevant to the question. Two things that you may think are relevant, but when you read it a little more carefully, you realize, oh, wait a sec, even though I have that given to me, I don't need that. So be conscious of that as you're working on this question, please.